I wanted to thank the organizers for the invitation. And I'm going to tell you about some work on contact topology in higher dimensions, which is joint with Klaus Niederkrüger and Paolo Ghiggini. So I will get to the main, the main statement is essentially the title, but I will get to a more precise version of this in a little bit. Let me start with some general background, which I think the experts will already know, but some of the students will not yet know, about symplectic fillings of contact manifolds. So this is part 0 of the talk. So one of the ways that one can think of contact geometry as a natural subject to study is that contact structures arise on boundaries of symplectic manifolds. So if you already believe that symplectic manifolds are something natural to study, this is one way that contact geometry comes up. For instance, if I have a 2n-dimensional symplectic manifold W, and let's call the boundary M. And now there's a convexity condition that we often talk about, namely, let's see, I've got other colors here. So I assume I have a vector field pointing outward at the boundary and defined in a collar neighborhood of the boundary with two properties. So first, I already said the vector field V is transverse to the boundary and pointing outward. And secondly, it's a Liouville vector field, which means the Lie derivative of the symplectic form with respect to that vector field is the symplectic form again. So that's the definition of being a Liouville vector field. And we say in this case that the boundary is convex. Now, what does all that have to do with contact geometry? Well, another way of expressing this Liouville vector field, if you remember that the symplectic form is non-degenerate, and therefore it gives you a one-to-one correspondence between vector fields and one forms. So let's look at the dual one form, which you define as lambda equals omega v acting on whatever. So these conditions on the vector field then give us the following in terms of the one form, namely, if I denote by alpha the restriction of lambda to the boundary, I'm running out of space. This is a contact form. Okay. That's equivalent to the condition that V points transversely outward at the boundary. And while being a contact form, remember that the contact condition says alpha wedge top dimensional power of d alpha is a volume form, and positively transverse means that that's going to be a positive volume form for the boundary orientation of M. And the fact that V is a Liouville vector field translates via Cartan's identity into the fact that lambda is a primitive of omega. So omega is exact near the boundary. I don't have to assume that omega is everywhere exact, because I'm only assuming that this vector field exists near the boundary. Near the boundary, omega is exact. So the induced contact structure, of course, is kernel of alpha. Contact structure. And one of the reasons why I always think the contact structure is a natural thing to think about in this picture is that a lot of what I've just said is non-canonical in some sense, right? There is not a unique Liouville vector field pointing transversely outward at the boundary, but the condition of being transversely outward at the boundary and being Liouville, these are both convex conditions. So there's a contractible space of choices there. And if you choose a different Liouville vector field, you'll get, as a result, a different contact form at the boundary, but it's belonging to a contractible space of choices. So in particular, it's connected. That means the induced contact structure is uniquely defined up to deformation. And then by Gray's stability theorem, that contact structure is unique up to isotopy. Okay? So in that sense, we often abbreviate this situation by saying boundary of W omega equals M psi. where psi is understood to be defined up to isotopy. So I just want to state there's many known results about fillings, and of course it's a natural question. If you're given a contact manifold, what are all the possible symplectic manifolds that can fill it in this sense? And there's a lot of results about that in dimension 3. There are a few much less precise results about that in higher dimensions. Really the main one is what I want to start out with quoting here, known as the Eliashberg-Floer-McDuff theorem. So this was proved in a paper of McDuff's in 1991 and attributed also to Eliashberg and Floer. And that states that all symplectic fillings W of the standard contact sphere and one way of understanding what the standard contact sphere is, by the way, is it's what you get in a natural way at the boundary of the standard symplectic ball. Okay? You can take a Liouville vector field that points radially outward. That induces a certain contact structure on the boundary, so that's the standard contact sphere. The statement is all symplectic fillings of that with an additional technical condition, namely symplectically aspherical, so omega vanishes on all two spheres. They're all diffeomorphic to the ball. Or I'll write it as the disk, D2n. So that's the strongest result we have in higher dimensions about symplectic fillings. And in dimension 4, we do know a lot more than that. We can say that all fillings of the standard 3 sphere are symplectomorphic to some, well, so either the ball with its standard symplectic structure or some deformation of this, which you would obtain just by moving the boundary to a different star-shaped energy surface, something like that. Okay, so that's a much stronger result. The reason we get a much stronger result is that theorems like this are proved usually using pseudo-holomorphic curves, and pseudo-holomorphic curves are a much stronger tool in dimension 4 because you have intersection theory. You don't have this in higher dimensions. What you usually get instead is some kind of homotopy theoretic information. And what the argument of Eliashberg, Floer, and McDuff actually does is it proves that if you have a filling with these properties, then first of all, it has to be simply connected. And then secondly, it has to have second homology equals 0, and third homology equals 0, and so forth. And so you combine Hurevich and Whitehead's theorem, and you find out that the thing must be contractible. And at the end, you can use the H-cobordism theorem to prove that it's actually diffeomorphic to the disk. So there's some very serious differential topology coming in at the end. Really what's happening is you're computing the homotopy type of that filling. And that's the best kind of result that one can usually hope for in higher dimensions. So my talk is not really going to be about fillings. That's not the essential point of it. But I needed to discuss this a little bit as background. I'd call it a digression, except it was the beginning, and digression shouldn't be at the beginning. But let's get actually to the main subject now, which is contact-connected sums. So contact-connected sums, in the first place, I just want to tell you that there's a natural way of taking two closed contact manifolds of the same dimension and producing a contact structure on the connected sum of those two manifolds. To understand in the contact category how this works, I think the simplest thing to say is it's a special case of a more general type of handle attachment. So by this I mean, imagine I've got two contact manifolds M1 and M2 of the same dimension 2n minus 1. And let's build, first of all, the trivial cobordism over both of them. That has a natural symplectic structure on it. And now I want to attach a one handle. So one handle, I'm going to write this as a slightly more general way. Let's say it's a K handle. So disk of dimension k times disk of dimension 2n minus k. But for the case k equals 1, right? So one can do this in general for any k less than or equal to n, such that you get a nice symplectic structure on the handle. There's a very precise model that one can write down, and it has sort of a nice Morse theoretic description. One of the ways that you get symplectic structures on fillings in particular is from plurisubharmonic functions. So this is the theory of Stein manifolds, which I don't want to go into. But if you think of this in terms of a plurisubharmonic function, you have sort of the natural Morse function that has a critical point at the intersection of the core and the co-core of the handle. And the core of the handle is a stable manifold of gradient lines converging to that critical point. Co-core is the unstable manifold. Okay? And you have sort of a hyperbolic picture of a gradient flow around that. So you can see in particular, with plurisubharmonic functions, one of their nice properties is that the gradient is a Liouville vector field for the induced symplectic structure. So you can see actually why you get convex boundary in this picture, because the gradient flow is going to be transversely outward at the new boundary of the thing you've attached. It's going to be transversely inward at the place where you're attaching it to the original manifold. Okay? So the definition of the contact connected sum is essentially it's what you get by doing this construction with a one handle with its nice choice of plurisubharmonic functions. So that gives you a Liouville vector field. The Liouville vector field, of course, corresponds to a Liouville one form, which restricts to the boundary as a contact form. So that induces the contact structure that you have at the boundary. You have to be a little bit careful, of course, about smoothing corners. But it's pretty easy to see in the picture why that works. If you smooth this corner, the fact that this vector field is pointing diagonally through the corner means it's also going to be pointing transversely through the smoothed corner. So it's not so easy to just write down formulas for what the contact structure looks like after this, but in the picture at least we can see the Liouville vector field, so we can see that there is a contact structure. So what you get from this, in the case of a one handle, is there is both a contact structure on the connected sum, and additionally a symplectic cobordism from the disjoint union of the original two things to the connected sum. More precisely, it's a Weinstein or Stein cobordism. Okay. So now let me recall a few things that are known about the contact connected sum and have been known for a while. So conveniently for me, John mentioned already this dichotomy between tight and over-twisted contact structures in dimension 3. Tight means rigid in the sense of not flexible. Over-twisted means everything you want to know about classification of contact structures you can understand in terms of homotopy theory. So there's no real contact geometric content. Okay? Tight is the antithesis of that. It's where the interesting stuff happens. Now, in about 1997, Vincent Collin showed the following about tight contact structures and the connected sum. First of all, if you have two contact structures that are both tight, then their contact connected sum also is tight. All right, I'm going to follow John's established pattern and at this point ask the question, is that true in higher dimensions? Right. So only in the last few years, we have a definition, thanks to Borman and Lieshberg-Murphy, and also further work by Casals and Murphy and Presas to simplify that definition. We have a notion of over-twistedness in higher dimensions. We have a flexibility theorem, but we don't have methods at our disposal so far to prove something like this about the contact-connected sum. That's completely open. But another result is that you can decompose non-prime tight contact manifolds in dimension 3. So if I have a connected sum of M1 and M2 with a tight contact structure psi, then Colin tells you that actually that tight contact structure is obtained from contact structures on M1 and M2 by this process I just described. So psi is isotopic to connected sum of some psi1 and psi2 for some tight contact structures on those two sum ends. Okay? The fact that they're tight is obvious. If they were over-twisted, the connected sum would also have an over-twisted disk in it. So that part is not special. But the fact that you can decompose them is. And it's actually pretty easy to see that it's not true without assuming tightness. That's because of flexibility. So if you believe in flexibility already, what would this require? Well, you've got a connected sum. So you imagine that, let's see if I can make use of this. Somewhere in your connected sum, there's this tube that has a two-sphere in the middle of it. And you want to split that apart. And glue a couple of 3 balls to those new boundary components after you've split it apart. So if you can do that, and you can then extend your given contact structures over those 3 balls that you glued in, that's what you want. That would mean that the contact-connected sum of those two extended contact structures is this one you started with. So it's easy to see that topologically, sometimes you can't do that. Right? You've got some contact structure along this two-sphere here. And, well, if you parallelize the 3-manifold, a homotopy class of 2-plane distributions on S2 is the same thing as a map from S2 to S2. So that has a degree. Its degree had better be 0 if you want to be able to extend that over the 3-ball. If it's not, then you simply can't do it. So there are some homotopy classes of 2-plane distributions where it's impossible. And flexibility tells you that those homotopy classes always have an over-twisted contact structure in them. So there's a slightly non-trivial thing hidden behind this statement that those homotopy classes never contain a tight contact structure. Okay? So the real question I want to address in this talk is that second statement true in higher dimensions? If you're given a tight contact structure on a connected sum, does it always decompose with respect to the connected sum? And that one, fortunately, I can answer. The answer is no. So in dimension greater than 3, in any dimension greater than 3, this is not true. And here's a more precise statement. So this, as I said, is joint with Ghiggini and Niederkrüger. And I guess I should say 2016. It was just recently published. Suppose n is greater than or equal to 3, and I have a 2n minus 1 dimensional almost contact structure, or almost contact manifold. So almost contact means the homotopy theoretic data underlying a contact structure. If I were in dimension 3, I would simply mean a homotopy class of oriented 2-plane fields. In higher dimensions, I have a little more data than that. What you have in general, you have both a co-oriented hyperplane field, and remember that d alpha is, if alpha is a contact form, d alpha is symplectic on the hyperplane field. So you get also a homotopy class of a symplectic bundle structure on that thing. that data together is what we call an almost contact structure. It's the homotopy theoretic data that you always have to have if a contact structure exists. So let's suppose I have that, and I call the almost contact structure phi. So I want to assume such that right, so first of all, some topological assumptions. M is not a homotopy sphere. But it admits a Morse function with unique critical points of maximal and minimal index and otherwise only index n minus 1 and n. Right, so there's potentially critical points of 0 and n minus 1 and n and 2n minus 1 with the maximum and the minimum being unique. Just to convince you this is not a statement about the empty set, I should say, for instance, you can take any S minus 1 fiber bundle over Sn, and it will satisfy these conditions. And the statement is then that the connected sum of M with reversed orientation with M itself admits a Steinfillable, which implies tight, contact structure psi, which is in the homotopy class of the connected sum of the two almost contact structures. So I'll write that as phi bar connected sum phi. Phi bar is just the same almost contact structure on the same manifold with the ambient orientation reversed. That's what my notation means. And you can take a connected sum of those. In that homotopy class, then you have a tight contact structure, but it is not something obtained by a contact connected sum. So it is not isotopic to any psi1 connected sum with psi2. Psi1 on minus m and psi2 on m. Okay. Any questions about the statement before I take it away from the screen? Okay. So here's a little bit more background now. Yeah. Mm-hmm. On M, yes. So M is a given manifold that has a Morse function with only these critical points.
How much general is this condition?
I don't know, but it works for a sphere bundle over a sphere in particular. So there are things. I mean, it's also true for the ordinary sphere, where you can assume there are no critical points of index n minus 1 and n. But I ruled that out because I said I don't want a homotopy sphere. OK. So let's do a little more background on symplectic fillings, and in particular Stein fillings. So I don't really want to go into saying what a Stein filling is if you haven't seen it before, but for now you can just assume it's a particular class of symplectically aspherical symplectic fillings, the way I defined before. So there's a result of Lieshberg from 1990 that says in dimension 3, it's very easy to characterize what the Stein fillings of a connected sum are. At least if you know what the Stein fillings of the summands are. So I'm going to have to use some new paper. So the statement is that every Stein filling of the connected sum of M1 and M2 is the obvious thing you might imagine if you understood the picture of the Stein cobordism from the disjoint union to the connected sum. Namely, you just take a Stein filling of M1 and a Stein filling of M2, and you attach the one handle. So that gives you a Stein filling of the connected sum of the two things. So that's a beautiful result. And I want to remind you a little bit of how the proof goes, because it was actually the reason we came upon our result about not everything being a contact connected sum is that we were trying to prove something else that was meant to be a generalization of this to higher dimensions. So how does this work? So we have this one handle, d1 times d3, and at the center of it, or rather the boundary of the co-core, is a particular copy of d3, or the co-core itself is a copy of d3. Boundary of that is what's called the belt sphere. And the belt sphere, if you think about understanding contact structures in 3 dimensions in terms of the foliations that they induce on embedded surfaces, this produces a very nice picture. We have a 2-sphere with an oriented singular foliation that has 2 singularities where the contact planes are tangent to that sphere, and the 2 singularities are then connected by smooth leaves that form longitudes. So that's the oriented singular foliation you get on the belt sphere. Now you have to use some analytical technology. The proof is based on Gromov's theory of J-holomorphic curves. So if you're given a filling of this connected sum, you choose a tame, almost complex structure on the filling, and you consider the moduli space of J-holomorphic disks into the filling with boundary on the belt sphere, minus the singular points. So analytically, the reason this works is that once you take the singular points out of the belt sphere, it gives you a totally real submanifold of this almost complex 4-manifold. And totally real, that's a nice boundary condition for J-holomorphic curves in general. You have all this elliptic theory that tells you the problem is Fredholm. So moduli spaces under the right conditions of genericity and so forth will be smooth manifolds of a certain dimension that you can compute from versions of the Riemann-Roch formula. So there's all this technology that fits into place. And this situation, it tells you that the moduli space of these disks is a one-dimensional manifold. And there's also a precise construction one can make finding specific disks that exist in the neighborhood of the singularities. So I'm trying to draw circles around the singularities. One can show that those are precisely the boundaries of explicitly constructed J-holomorphic disks. One can just write down. And they are part of that moduli space. Now, away from the singularities, we don't have anything quite so concrete. We don't know what the disks look like. But we have much more general results that say that moduli space is compact, and it's a one-dimensional manifold. We know what compact one-dimensional manifolds look like. So we get this one-dimensional family of disks that fill up some three-dimensional space. And that three-dimensional space is exactly the co-core of the handle. What this does, the family of J-holomorphic disks discovers for you the co-core of the handle sitting in the picture, although you didn't know it was there, right? You only knew in the first place that the boundary of that co-core was there, because that's part of the connected sum at the boundary. Right? So that's the main step, and the rest is working with that information to actually see the handle symplectically in the picture. All right. So, yes? I could have said compatible, but tame is also good enough. Yeah. In this case, it doesn't make any difference. All right, so let me mention also by way of context another result that appeared relatively recently. Bowden, Crowley, and Stipschitz thought about how likely it is for this theorem to be true in higher dimensions, and came up with something that at first looked like evidence against it. And it says that in some sense, topologically, this is not true in higher dimensions. Topologically means talking about almost contact structures instead of contact structures. What you can say is there exist Sn minus 1 bundles over Sn. Here I have to assume n greater than or equal to 2. I think they actually assumed something stricter than that. But in any case, there exists some with the property that, let's call the thing M, with non-fillable almost contact structures phi, such that the connected sum of minus M with itself, with this connected sum of almost contact structures again, is Steinfillable. So in other words, here we have an almost contact manifold that is Steinfillable, but it's definitely not true that all its Steinfillings are obtained by Steinfillings of the summands and then attaching a one handle, because the summands themselves are not fillable. Okay, so that sounds very pessimistic until you think a little bit further about what this statement really says. And there's one key point. It says almost contact instead of contact. So it never actually specifies what contact structure you're working with. There can be multiple distinct non-isotopic contact structures in the same homotopy class of almost contact structures. What this is saying is there exists this almost contact structure phi. Well, or let's put it a slightly different way. There exists an almost contact structure on the connected sum, which is Steinfillable, even though the summands are not. But this Steinfilling induces some contact structure on the boundary, and we have no idea which one that is. We only know its homotopy class as an almost contact structure. So in particular, we do not know whether the boundary of that Steinfilling is a contact connected sum. Okay? It might actually not be. And actually, a corollary of our result is that the contact structures at the boundary of the filling of that connected sum are not contact connected sums. So combining these two results, what we see is it's not impossible that Eliashberg's theorem could really be true in higher dimensions. Okay? The reason Bowden, Crowley, and Stipschitz were able to find what looked like evidence against it is actually that because our theorem is true, because connected sums don't have to be contact connected sums in general. Okay. So now to move on and talk a little bit about the proof. The question we actually wanted to answer when we started our project was, is Eliashberg's theorem homotopy theoretically plausible in higher dimensions? Right, and we thought that was a reasonable question because, again, if you think about what's known about fillings of higher dimensional contact manifolds, there isn't much except for the Eliashberg-Floer-McDuff theorem, and that's a classification up to homotopy type. So homotopy type seems like something reasonable, where you could prove something. And so the more specific version of this question is the following. If I have a Stein filling W of a contact-connected sum M1 sharp N2, being a connected sum means it contains some special sphere, the belt sphere, at the center of a tube. Is it then true that that belt sphere must be null homotopic in the filling? So the answer to this question is, I don't know. Because in that sense, our project failed. We weren't able to prove that. We proved it in dimension 5, so we were a little bit happy about that. We proved it in dimension, well, something similar to that we proved in dimension 7 under some extra assumption. And then we got very frustrated at how hard the problem seemed. So I think that's all there is in the first version of the paper we put in the archive. It doesn't even have the connected sum result in it. And later we realized, after we'd looked at what Bowden, Crowley, and Shipshitz did, that we knew how to do something more interesting. So for the students among you, the moral of this story is if your project fails, don't discount the possibility that you actually proved something more interesting than you intended. You may need to step back a bit. Now, what we wanted, though, is not just a result about connected sums, because if you think about why you might expect it to be true, we knew how Eliashberg's proof in dimension 3 worked. And the idea, right, if you've got this boundary that looks like the boundary of something with a handle attached, but let's not say one handle, let's in general say a K handle. So the belt sphere here is the boundary of a 2n minus k disk. So it's a sphere of dimension 2n minus k minus 1. Now Eliashberg's proof works because that's a two-dimensional sphere which turns out to mostly be a totally real submanifold in an almost complex four manifold. So under what circumstances could you hope for that thing to be a totally real submanifold? It would have to be half the dimension, which usually that's not, right? And in the connected sum case, k equals 1, that will actually never be half the dimension except in dimension 4. But maybe you could get something just as good, because if that's something of larger dimension, it still might contain totally real submanifolds. It might even, if you're lucky, be foliated by totally real submanifolds. So in order for that to be plausible, we observe that could contain a totally real submanifold. If and only if 2n minus k minus 1 is greater than or equal to n, which is equivalent to the condition k is less than or equal to n minus 1. And that's what's known as subcritical surgery. And if you know a little bit more of the context of things that have been proved in the past, it sounds very plausible that you would be able to say something close to classification of fillings for things obtained by subcritical surgery. So in dimension 3, it's known that anything subcritically fillable has, in fact, a unique Stein filling. There's flexibility of Stein structures in the subcritical case, all sorts of results like this. So the subcritical case is special. And so it does seem quite reasonable that one might be able to prove some classification result about fillings in this case. But we're not just going for classifying fillings of things that are subcritically fillable, right? This is anything, take any contact manifold at all. Maybe you know what its fillings looks like, maybe you don't, but then perform subcritical surgery on it. So the question then is, if you do that and then you have a filling of the new thing, does the belt sphere have to be null homotopic? All right. Let me say a little bit more about what boundary condition we end up with if we do this, because this it leads again to the whole topic of submanifolds, of contact manifolds. And this is a slightly different type than I think you'll probably be hearing about in John's talks. In a 2n-1 dimensional contact manifold, we end up with the notion of what we call a Legendrian open book. Which we abbreviate by LOB. So what's this? This is a closed submanifold L of dimension n. So that's one dimension larger than the dimension of a Legendrian submanifold. And it comes with the data of an open book decomposition. So that's a fibration of L in the complement of some submanifold of codimension 2, the binding called B, fibering over S1, with the fundamental property that all pages are Legendrian submanifolds. So in other words, all the pages are everywhere tangent to the contact structure. It's a consequence, by the way, of that definition that the binding itself is an isotropic submanifold. The binding is also tangent to the contact structure. So I should throw in a really important word of caution for those of you who are used to hearing about contact manifolds and open books in the same sentence. I don't mean the same thing that people usually mean here. This is completely different from Giroux's notion of open books supporting contact structures. I'm not talking about an open book on M. I'm talking about a submanifold of dimension a little bit more than a half, which is itself equipped with an open book. Right? In Giroux's notion, the pages of the open book are essentially Liouville hypersurfaces in the contact manifold. They inherit the structure of a symplectic filling or even a Stein filling in nice cases. Here, it's sort of orthogonal to that point of view. The pages have the structure of a Legendrian submanifold, each one. So it's sort of a very non-generic object, but it arises in certain very natural situations, one of which is the thing I already drew, where you have the two-sphere with these two poles and an S1 family of longitudes connecting them to each other. That's the characteristic foliation of the belt sphere in a three-dimensional connected sum. That's the simplest example of a Legendrian open book. The binding is these 2 points where you have the singularities, and you have an S1 family of pages that have the topology of the interval connecting them. Those are, of course, Legendrian submanifolds. Okay? That's the simplest example. It turns out that in general, if you do a subcritical n-1 surgery, you see, again, precisely this kind of picture on the belt sphere of that surgery, except it's higher dimensional. It naturally has a Legendrian open book. And what can also be shown with somewhat more effort is that for any subcritical surgery at all, the belt sphere can be decomposed into a family of Legendrian open books in this sense. Okay? I don't want to spend time on this, but I will say that takes more effort because we were stuck on that detail for about a year in this project. And we had to come up with a fairly creative deformation and actually view the belt sphere not as the boundary of a smooth ball, but as something more like the boundary of a polydisk, having a corner on it, in order to see the family of Legendrian open books. From the right perspective, it's a very clear picture, but it took a while to find the right perspective. So I'm going to suppress that detail. What you have, in general, if you have a Legendrian open book, is, well, the same thing that Eliashberg and originally in Gromov's 1985 paper, there's also a version of this. In the neighborhood of the singularity, there is this family of holomorphic disks. So same thing turns out to be true in higher dimensions. You get what's traditionally called a Bishop family of holomorphic disks. Which you can think of mapping into, even if you don't have a filling in the picture, you can just think of the bottom half of the symplectization of the contact manifold as the target space for these disks. And the boundary condition is something in the boundary of that half symplectization looking like the Legendrian open book minus its binding. The binding is the singular part where the totally real condition fails. Everywhere outside the binding, this thing is a totally real submanifold. And a particularly nice property you have with these Bishop disks comes from the maximum principle for subharmonic functions. Now, the way this works in dimension 3 is if you think about a holomorphic disk mapping into the symplectization and just look at the part of it that's mapping into the half line, the reals. Okay? The fact that the disk is holomorphic means that's a subharmonic real-valued function. So it cannot have a local maximum. And there's even more to it than that. At the boundary, the normal derivative of that function has to be non-zero. Now, if you look at how J is constructed, that translates into a statement about the restriction of U itself to the boundary, that that map of the circle will be transverse to the contact planes. And actually, that whole discussion carries over to higher dimensions in a very nice way. So that boundary is always transverse to the contact planes, which means, in fact, since the pages of the lob are Legendrian, the thing is also transverse to all the pages. Now, the explicitly constructed disks all have the property that they're going exactly once around the whole family of pages. So then that's going to be true for every disk in the moduli space. And in fact, for those of you who know about Gromov compactness and the things you have to worry about to prove compactness of a moduli space, this is why nothing goes wrong. You prevent bubbling of holomorphic disks because of this topological condition that you're always going transversely through each page exactly once. So the summary is that once you've understood this boundary condition, everything works out exactly as nicely as it does in the low-dimensional case. All right, so now I can state what I will call the main lemma. Yeah. We don't, and we don't care. Yeah. No, indeed. So there's no positivity of intersections. That's the one thing that doesn't work out as nicely. But indeed. So that's the main reason we never hoped to prove anything like the belt sphere is the boundary of some embedded disk. We only hoped to prove that it's null homotopic. Right, right. So yeah, instead of diffeomorphisms, you can talk about maps of degree 1, which I will do in a moment. Okay, so main lemma. Once you believe me that the belt sphere can be deformed into a smooth family of Legendrian open books, I'm going to say assume we have this, let's say, n plus m dimensional belt sphere sitting in our contact manifold M psi, which is presented as the boundary of some symplectic filling W omega, which is symplectically aspherical. Then for generic tame almost complex structures J on W omega, there exists a compact oriented n plus m minus 1 dimensional moduli space called M bar of J holomorphic disks. Oops. Mapping into W with boundary mapping into the belt sphere. Right? And to be more precise, I should say the belt sphere minus the bindings of those Landrian open books, since that's where a totally real condition fails. I'm cheating a little bit, and I'm going to include in this moduli space some singular maps that are not strictly J holomorphic, but are just constants that you have mapping into the binding. That's part of the compactification that I'm implying by putting a bar over the M. So don't worry about that unless you really want to. Now, such that the boundary of this compactified moduli space is a sphere of dimension n plus m minus 2. And there exists an evaluation map so the evaluation map just takes each holomorphic disk and a point in its domain and sends you to the image of that point for that disk. And it's easy to show that basically by construction, looking at this product of the moduli space with the disk as a manifold with boundary and corners, this sends the boundary to the belt sphere again. So we get a map to the filling with boundary going to the belt sphere. I want to say that that is, so an evaluation map that is a diffeomorphism on a neighborhood of the preimage of the binding. I'm being a little bit sloppy. I should say restricting to the boundary and looking at a neighborhood of points that are sent to the binding. This thing is a diffeomorphism. So in particular, its restriction to the boundary is a map of degree 1. All right, so now I can go ahead and prove theorem 1. Let me put it back in front of you for a moment since I have this wonderful technology I can use. Okay. So theorem 1 said we've got this almost contact manifold, which is not a homotopy sphere, admits a Morse function with critical points of index 0, n minus 1, n, and 2n minus 1, where the local max and local min are unique. And then we claim that that particular connected sum minus m with m has a Steinfillable contact structure on it that is homotopic to something that's a connected sum, but it's not isotopic to any contact connected sum. So why is this true? I should give a little bit of credit here to Bowden, Crowley, and Stipschitz. Because we're borrowing a construction from their paper and just using it for a slightly different purpose. So the construction is the following. So we're given M with the stated properties. Let M star denote the complement of a ball in M. And this Morse function exists by assumption, which has a unique local min and local max. I can position the local max to be in that ball that I removed. So the upshot is then I can choose a Morse function f on M star with critical points of index 0, n minus 1, and n only, and with gradient transversely outward at the boundary. And the other assumption was that I have an almost contact structure. So what can you do with an almost contact structure on M? Well, I'm getting slightly ahead of myself. Let me first go one dimension up and define what will be my Steinfelling. Let W equal the product of M star with an interval. Okay? So I've got at either ends of that interval, I've got copies of M star or itself with orientation reversed, and they are connected to each other by a tube of spheres, boundary of M star times an interval. So after you smooth the corners, that is a connected sum. And the next thing I want to do with it is say that since I have an almost contact structure on M, there's a natural homotopy class corresponding to that of almost complex structures. J on W. And my Morse function f gives me a Morse function on W with critical points of index 0, n minus 1, and n again, and nothing larger than n. Okay, so experts will by now see where I'm going with this because they know another old theorem of Eliashberg's that says since I have an almost complex structure, and I have a Morse function with no critical points of index larger than n, my almost complex structure is now homotopic to a Stein structure. On W, which is filling some contact structure psi, which is then homotopic to this connected sum of almost contact structures on the boundary. Okay? So the only thing I have left to show you is that that particular contact structure doesn't arise as a contact connected sum. So imagine that it did. What does it mean to be a contact connected sum? Well, we can see, of course, topologically what the belt sphere would be. Going back to the previous picture, right? The belt sphere would be the center of the tube. I have 0 times boundary of M star. So question is, can you assume even up to isotopy that that particular sphere looks like the belt sphere of a contact connected sum? Does its contact structure in a neighborhood look the way we get from a Weinstein one-handle? Because if it does, then you can do all the things that I described already with this moduli space of J holomorphic disks. So if that belt sphere exists in there with all the properties I've talked about, then we consider that moduli space again. We have the evaluation map. Which takes us to the filling m star times interval, and it takes the boundary to the belt sphere, which is boundary of m star times 0. So that's what I got from the main lemma, and it has certain properties like restricting to the boundary gives you a degree 1 map. Now compose that with the obvious projection, getting rid of the interval. We get a map to m star, comma, boundary m star. So that composition, let's call it phi, is now a map of degree 1. And on the boundary is a diffeomorphism in some neighborhood. So since I'm out of time, I'm just going to tell you, you figure out the rest if you go back to the Eliashberg-Floer-McDuff theorem and read the proof in McDuff's paper. Because what they did was consider some moduli space of holomorphic curves such that the evaluation map from there to the unknown filling has precisely the kinds of properties that we have here. We've got a map of degree 1 between manifolds with boundary, which looks like a diffeomorphism in some small neighborhood. So the rest is essentially an exercise in algebraic topology. I'm just going to say by the argument of Eliashberg-Floer-McDuff. We get the same conclusion that they did. They were trying to conclude that their unknown filling is contractible. What we get is that m star must be contractible. So we've got a contractible space that was obtained by removing a ball from something that was, by assumption, not a homotopy sphere. That's the only assumption left that I haven't used. This is where I have to use it, because that implies that M is a homotopy sphere, and I get a contradiction. That's where I'll stop. Thanks.
Questions for Grace? One way to find this Pythagorean open book. So if I give you some manifold of your contact manifold in modular time, no.
Presumably not. No, I think it's a very special condition. I think it arises naturally in specific contexts such as this. I don't know what other contexts, actually. What I can say is, of course, since Niederkrüger is a co-author, it's closely related to some of the things that come out of his work on higher dimensional filling obstructions, like the Plastikstufe, right? Which is also a fairly non-generic condition. Yeah.
So this particular example, we have your sphere that you're trying to cut along, filled up by these blobs, and that's the convex of the sphere. Is that a general property? Do we have something that's fully by blobs that has to be convex? I mean, convex incompatibilities are hard to understand.
It's not immediately, I've never thought about it, so it's not immediately obvious to me that this one is convex. Is it? Yeah, okay, I can see that it is convex. No, if it's a general property, I have no idea.